Hello there. In the previous video we introduced what we called the Digamma function. So the Digamma function, or the psi function of x, is defined to be equal to the logarithmic derivative of the gamma function. So one can find that this is going to be equal to gamma prime of x divided by gamma of x. So in this video we're going to be looking at just a couple simple identities on how to take the integral of the digamma function or the integral of the quotient of the gamma function and the gamma function. Keep in mind that the integral of the derivative is not necessarily equal to the derivative of the integral, so we're not going to take anything as an easy assumption. Alright, so the first example I'm just going to do in a very straightforward and direct way, just in case you are not already familiar with the gamma function and its properties. And we're going to find the integral from x to x plus 1 of the digamma function of t dt. And we're going to assume that x is going to be some positive real number. So we can rewrite digamma as what it's defined to be. So the integral from x to x plus 1 of gamma prime of t over gamma t dt. And now we can use u substitution. So we have the derivative of gamma and gamma itself. So we're going to let u be equal to gamma of t. So that means du is going to be gamma prime of t dt. Therefore dt is going to be equal to du divided by gamma prime of t. Right? And we can easily shift our values of t. So if t is equal to a, then that means u is going to be equal to gamma of a. Right? That's very easy to prove. So that means our integral is going to be equal to gamma of x to gamma of x plus 1 of gamma prime of t over u times the differential of u over gamma prime of t. So our gamma prime of t's cancel, and we're just left with the integral of 1 over u du, which we know to be the natural log of the absolute value of u plus some arbitrary constant. But it's definite, so we're going to integrate this as u goes to gamma x plus 1, as u goes to gamma of x, and then we're going to subtract these values. So that's going to give us what? So then we have the natural log of the gamma x plus 1 minus the natural log of the gamma of x. And then we can use the properties of logarithms here. So we have the natural log of gamma of x plus 1 all over gamma of x. And now we can use the definition or the main property of gamma, which is used to relate to the factorial. So gamma x plus 1 is the same as x gamma x, and on the bottom we just have gamma of x. So the gamma of x is cancelled, so therefore we have what our integral of interest is equal to, so that we have just the natural log of x here. And we have the integral from x to x plus 1 of digamma of t dt is just equal to the natural log of x. Very, very elegant and simple relationship. So a very easy corollary to prove from this is the following. So that means the integral from 1 to 2 of digamma of x dx is just going to be equal to the natural log of the lower limit, which in this case is 1, because the difference between these is just 1, which is of course equal to 0. Right? So that's nice. So let's make this integral a little bit more interesting. Let's do, say, the integral from 3 to 5 of the digamma of x dx. Alright, so how can we approach this? Well, we know that this integral is equivalent to the integral from 3 to 4 plus the integral from 4 to 5 of digamma of x dx, right? So the integral from 3 to 4 is just going to be equal to the natural log of 3, and the integral from 4 to 5 is just going to be the natural log of 4. So this is just going to be equal to the natural log of 12. Right? So that's the integral from 3 to 5 of digamma of x. And of course you can extend this to any integer, I guess, right? So we can say, okay, so here's an exercise for you if you want. So let us assume we have a to a plus or some multiple of a. well, not necessarily a multiple of a, but a plus some constant k, right? So what is that going to be equal to? And let's assume that k is a natural number. So this is going to be equal to the integral from a to a plus 1 plus the integral from a plus 1 to a plus 2 all the way out to the integral from a plus k minus 1 to a plus k of digamma of x dx. So this is of course just going to be equal to the natural log of a plus the natural log of a plus 1 all the way out to the natural log of a plus k minus 1. So that means this is just going to be equal to the natural log of the product from k is equal to, let's not do k, let's do L as our index. So the integral from the product from L is equal to 0 to k minus 1 of a plus L. Right? It's a very simple compact relationship. Now, what if it's not an integer or a natural number that's being added to the base, right? So let us assume we have something weird, like the integral from 2 to, say, 5 halves. So the integral from 2 to 2.5 of digamma of x dx. So we know, we can show that this is just going to be equal to the natural log of the gamma of x, evaluated as x goes to 5 halves, minus as x goes to 2. And let's see what this actually comes out to. So this is going to be the natural log of gamma of 5 halves minus the natural log of gamma of 2. So remember, gamma of 2 is the same as 2 minus 1 factorial, which is 1 factorial, and the natural log of 1 is going to be 0. So this is just going to go to 0. No big deal there. And then we have the natural log of, now we can split this 5 halves interior of the gamma function up very nicely. So using that additive relation of gamma, this is just going to be 3 halves times gamma of 3 halves. And then we can break gamma of 3 halves up into a similar way. So that's going to be 1 half times gamma of 1 half, right? And so this is just going to be equal to the natural log of 3/4 plus gamma, the natural log of gamma of 1 half, right? So as we should already know, natural log of gamma of 1 half is just going to be the square root of pi. So we have the natural log of the square root of pi there, and we have the natural log of 3/4 there, right? So this is just going to be equal to, you can rewrite this in one of many ways. So this is going to be 3/4 of the square root of pi, right? So very compact, nice relationship in closed form for that integral. Now, as we should already know, at the time of making this video, a lot of the values of gamma do not have a closed form, for example, gamma of a third, and things like that, things of that nature, right? So if you have something such as the integral from the square root of 2 to, say, pi of the digamma of x dx, then this is just going to be equal to, again, the natural log of gamma of x, evaluated as x goes to pi and as x goes to the square root of 2, right? So this is just going to be equal to the natural log of gamma of pi divided by gamma of the square root of 2. And if you know what the closed forms of those things are, then that would be wonderful. But currently we don't. So we can just leave that as the closed form representation. So as we see, integrating the digamma function is actually pretty nice because it's defined as a derivative of the gamma function. So that makes things really, really nice for us. Anyway, this is just another extensive video of the digamma function. Hope you enjoyed.